So let's talk about some examples to illustrate what we just talked about in a general sense. So we will consider a number of examples. The first example is about a constant coefficient second order differential equation. And as we have discussed, this arises in many contexts. And so in these examples, we want to stress a number of things. We want to first stress the fact that before we start with detailed analysis, we want to think about the problem. We want to anticipate what is going to happen. And so for this, an approach which is very important is to scale the problem so that we can express the general dependencies. And so we'll stress that, and we're saying this before you start the analysis. Let's take this as a systematic step. And then we will be illustrating a homogeneous solution and particular solution. And particular solution will be obtained by the variation of parameters method, and that together will provide a complete solution. And of course, we want to pause and interpret the solution as well. And so we'll begin with this very familiar example, mu double dot plus cu dot plus ku. That is defining the left-hand side of this equation, forced by right-hand side f of t, some arbitrary function of time. U dot is the first derivative, u double dot would be the second derivative, and mass spring damper systems in mechanical applications, vibrations, oscillation applications, and as well as in electrical applications of RLC circuits and other applications give rise to these equations with interpretation that we have seen before. And so it's this equation that we want to start from. So as we begin, we should take a look at the problem and ask, have we made the problem non-dimensional in a suitable way? This is the idea of scaling the problem so that we are making the best use of information that we can easily discern. So for example, in the problem that we're talking about, there may be a natural time scale. And so the point then is, have we made the units of time appropriately non-dimensional? And so we can redefine a new variable tau, which is a non-dimensional time, t over capital T, where capital T is a natural time scale. And so for these problems, you may recall that for a problem which is undamped, the natural frequency is associated with this time scale, t given by square root of m over k. And so we want to choose capital T as the natural time scale. And so we introduce a new derivative. We put derivatives d dt in terms of the derivative with respect to the new time, capital tau, which is a natural time scale. So through chain rule, we have this, and the first factor here by the definition is simply 1 over t. So note that dd tau is a derivative on the non-dimensional time scale. So of course, this would make the independent variable non-dimensional. We have to also non-dimensionalize the dependent variable, and so the question is, how should we scale the dependent variable u? And so here we need some more information about the problem. So let's define a specific problem with a specific initial condition that u at time of 0 is equal to u0. This is a given value of the initial displacement. And to simplify things, let's suppose that the initial velocity, the initial rate of change of u, is actually equal to 0. All right? So given this value, it's very natural to non-dimensionalize the velocity, this displacement by the initial displacement. So we can say that v then represents a non-dimensional displacement, u over u0. And so in terms of the new variable v and the temporal variation tau, we can state the initial conditions that v of 0 is equal to 1 by rescaling u in terms of v, and the time derivative of v at time t equal to 0 is 0. So we're going to be using these conditions for solving the specific problem. Let's define the complete problem, and then we will see what the benefit of this non-dimensionalization is. So here we have rewritten the original problem in non-dimensional terms. Differential equation stated in terms of v, dv d tau square, d square v d tau square, plus non-dimensional coefficient gamma, dv d tau plus v equals the right hand side, which is a non-dimensional forcing function. There's only one parameter that appears in this problem, gamma, which is a rescaled version of the coefficient c that was appearing in the problem, c over square root of m times k. And the initial condition is that v at tau equal to 0 is 1 and dv d tau is equal to 0. So note that in this non-dimensional version, we have only one parameter, gamma. Initial condition is unitless with 1 here and 0 here, and there is a single non-dimensional coefficient. Originally, if we go back and see, as the problem was originally stated, we had 4 parameters in it: the mass, the spring constant, and the dashpot or the damper value c. We had m, k, and c, and we had the initial displacement v0 or u0. We had 4 parameters, but by scaling the problem, what we are finding is that the solution depends only on this combination of variables. So if we can solve this problem, we have solved the whole family of solutions for arbitrary values of the 4 parameters that appear in terms of solutions that are given by just a single parameter. So this is an extremely powerful method. It allows us to find solutions to a larger class of problems by solving just one problem.